to be quantitatively accurate in theories for, let's say, DC resistivity or TC in a superconductor, even in relatively weak coupling systems, this can be an incredibly difficult task. And so what I thought is I want to take a step back, and I only have 2 lectures, so maybe I will give some broad perspective and some, try to come up with some general constraints, both on different kinds of unconventional metallic transport that you could get. And of course, given, that, mechanisms of T-linear resistivity are, of course, something that, keep a lot of theorists awake at night, I'm going to talk about some relatively well understood but elegant mechanisms that could lead to T-linear resistivity, especially in regimes that are not described by conventional Fermi liquids with a sharply defined Fermi surface, low energy quasiparticles, and so on. So that's the plan for today. And by the end of it, actually, instead of talking about general mechanisms, I also want to focus on a particular compound. Perhaps it's not as glamorous as the cuprates or TBG, but it has already sort of made an appearance, or at least a related compound has made an appearance in a talk yesterday by Leonid. And it turns out this is a compound which does exhibit some very unconventional T-linear resistivity with some Planckian scattering rates. And we can develop a quantitatively accurate theory for where that might come from. And it turns out that leads to some new questions that we must address if we really want to come up with general bounds on transport. So the plan for today is to mostly talk about transport, and tomorrow I want to say something about how do you think about making general bounds on superconducting TC. Now, for the purpose of these lectures, I'm only going to focus on 2-dimensional or quasi-2-dimensional systems. And hopefully, as the talk goes along, it'll become clear why that is. Today, I'm only talking about transport, right? So now, transport, it's one of the things that, there are a lot of experimentalists in the audience. You get a new material from your friends. That's probably one of the first things you measure. And often you discover some interesting behavior, maybe superconductivity, T-linear resistivity. And of course, it's controlled by the quantum mechanics of your strongly correlated systems. And in principle, it has information on all the, the ground state, the low-lying excitations. But, backing that up from the actual data is incredibly hard. And so, many experimentalists, I don't know who's the first one who's, they said that transport is the first thing you measure and the last thing you understand. And, in the cuprates, we have known about this mysterious, strange metallic T-linear resistivity forever. And, we are still arguing about what might be causing it. So I should also mention that I, typed up some notes. It's more like a stream of consciousness over the past couple of days, and it's online. I'm sure it has typos, missing references. So yeah, please take a look. And if you have any comments, get back to me. So as I said, I want to focus on transport in 2-dimensional systems. Now, if you just think about resistivity, and let's not worry about any microscopic theory of resistivity, you would start out by writing, there's a natural scale in the problem, which is the quantum of resistance. This is h over e squared. If you are thinking about any generic system, it depends on a whole lot of quantities. There are multiple temperature scales. Let's say if you're thinking about a metal in a solid temperature, there's an effective Debye or Bloch-Grüneisen temperature, and so on and so forth. So I'm just clubbing all of that into some T star. There are potentially multiple length scales of the problem due to mean free paths coming from disorder, interactions, and whatnot. If you're thinking about a magnetic field, it could depend on the magnetic field, phi naught is the flux quantum, and so on and so forth. Okay, but let's just think about 0 temperature. Okay, so at 0 temperature, you really have, let's ignore elastic scattering of impurities, 3 options. Rho can either be 0. So in a perfectly clean metal, there is no way a momentum can relax, so rho is 0. Or, of course, rho is also 0 in a superconductor. And you can have at 0 temperature an insulator, so rho is infinity. Or the other option is rho is order h over e squared. And there are some interesting, something like this also happens. Now, today I want to focus on transport in metals. And metals are very interesting objects. They're very gapless. they have a Fermi surface with lots of low energy excitations that gives rise to all kinds of power laws in the temperature dependence. If you think about most conventional metals, let's say copper or something like that, the dominant source of scattering, if you're thinking about DC resistivity, is electron-phonon scattering. I'll show you a plot of what the resistivity looks like in a second. And so then, when you see power laws, and in electronic solids, electrons are scattering off of everything, each other, disorder, phonons, maybe grain boundaries, who knows. You can get all kinds of, bizarre crossovers and so on. So why do we care about this messy thing? Well, because it turns out there is, there are a lot of compounds where something truly miraculous happens. Again, this is what people have been obsessed with. So this is data on one particular cuprate, whole dope cuprate, near optimal doping, LSCO. This is actually very old data from the 90s in a different cuprate. And it's not as if whole dope cuprates universally across doping regimes show this behavior. There are certain points in parameter space where this occurs, but you see this and you notice that starting from a very low temperature scale up to very high temperature scales, quite often up to a point at which the crystal melts, you see this very nice T-linear resistivity. Okay, just for reference, this is what the data looks like in copper. You also see T-linear resistivity. Now, interestingly, I was just talking to some students this morning, and it became clear that these days, the moment you see T-linear resistivity, there's a tendency to say, that must be a strange metal. Well, okay, depends to some extent on your definition of strange, but we don't think of this as a strange metal. It's a very well understood mechanism for T-linear resistivity, and we'll talk more about that. In Dmitry Maslov's talk, he already talked about electron-phonon scattering, and that's basically what is causing the T-linear resistivity in copper. The basic idea being, if you're above some characteristic temperature scale, which is for electron-phonon scattering, is set by the effective Debye energy scale or some Bloch-Grüneisen scale, the phonons are effectively classical. The phonons, they have an unbounded Hilbert space. You can describe their occupation in terms of the Bose-Einstein distribution. When the temperatures are larger than omega Debye, you can just keep exciting more and more phonons, right? So it effectively acts almost like a source of quasi-elastic scattering, and that is what gives you this T-linear resistivity, okay? Now, why is the data here or the data in the other cuprate not trivially explained by phonon-induced scattering? Well, there are many reasons for that, and I'll go through some of them. And then I'll talk about this mundane example of a material I told you about, which will lead us to, perhaps some questions on how or what are the possible loopholes that can take us around. This is a school, so I'm going to try and raise lots of questions for you to work on and think about open questions. I've tried to highlight them in the notes as well. Okay, so coming back to these examples, well, I'm sure you have seen what the unit cell of LSCO or BISCA looks like. I think Subir put up a picture of what crystal cell, unit cell for BISCA looks like. It has lots of atoms, meaning it has lots of phonon branches, right? And there are independent experiments from where we know that the electrons are coupled to multiple phonon branches. So as you heat the system up, you're crossing through many effective Debye temperatures for these different phonon branches. So as I said, electrons scatter off of everything. And this is basically the statement of Matheson's rule that I believe you also encountered. If you look at the total resistivity or the scattering rate, it's like all the resistors add in series. So you have electron impurity scattering, electron phonon, electron, and so on, okay? So as you scatter off more and more phonons associated with different energies, naively you would think that the temperature dependence of your resistivity will change and there will be some graph. For instance, what this particular data is trying to show is the red region is a regime where you might be able to explain the T-linear resistivity as being due to a particular phonon mode, but there's no way you can explain what the green part of the resistivity is coming from. And similarly, if you just keep going to higher and higher temperatures, there will be similar onset of other phonon modes. So how do you explain this relatively large range of temperature scales, which have just a single slope, so to speak? The other example, which is more recent, arises in twisted bilayer graphene, which you heard about last week. Again, there is a particular region in the phase diagram where the linear resistivity that shows up extends over a shocking range of temperature scales, almost from a few tens of milli-K to around 30K without any change in the slope, okay? And just for the sake of concreteness, this is what you would calculate for what the phonon dispersions might look like if you start from just the individual phonon modes in graphene and twist them, add the Moiré potential, they get reconstructed. So again, there's a whole bunch of phonon modes. If transport was determined by some kind of Mathieson rule, then you would expect there to be all kinds of crossovers as you go up in temperature, and yet you don't see any of that. Okay? Yeah.
Does one see a Mathieson rule sort of adding up octilinear slopes in conventional metals?
Like copper?
Well, maybe not elemental, so that there are a lot
of
phonon.
Actually, for the phonons, I'm not sure. In many of these compounds, you do see Mathieson rule, evidence of that, just by varying impurity scattering. Yeah. Well, I believe there's a paper by Sean and a former student of his, I think, where they talk about overdoped cuprates, where the slope does change, and they can explain part of the high temperature by phonons, but I'm not sure if they can really attribute a Mathieson. I don't know.
The question is about simple metals.
Yeah. I don't know. I mean, I don't know much about simple metals. Maybe that's the trouble. Okay, any other questions? Yeah. Yeah, I'm just focusing on this intermediate range where there's a broad region of dopings where it looks T-linear. Actually, I think Leonid is one of the co-authors of this paper. If you have technical questions, you should address them to Leonid. So this is, the color coding here, I'm not sure if it's visible, so the red is basically in very close to the nu equals -2 superconductor, right? All right. Right. So as I said, naive Mathieson type arguments would tell you that, the more scattering channels you add for electrons, the temperature dependence of the resistivity will keep increasing. And that doesn't seem to happen in at least two of these examples. Turns out that's also the case across many different unconventional metallic systems which exhibit linear resistivity. So this really was one of the main motivations for coming up with this idea that there might exist some fundamental bound on how large the scattering rate might be. Okay, the trouble is it's usually very difficult to have a very precise definition of what you mean by a scattering rate. So, okay, and I'll talk a bit more about that. That also touches on things that Peter Armitage talked about during the first week. But one of the early papers that really demonstrated the possibility that there might exist such Planckian bound goes back to this paper by Andy Mackenzie and collaborators, where they extracted a scattering rate. Okay, so now because this is going to be somewhat important, I'm just going to briefly tell you what they did. Now, on some level, if you want to extract a transport scattering rate, maybe the best way to do that is from optics experiments. So like Peter was showing during week 1, you measure omega dependence of conductivity, you get some Drude-like peak that has the width, that's the optical scattering rate. But unfortunately, optics requires much more effort. Again, to the experimentalist students in the audience, just try to come up with new methods to do optical conductivity across all kinds of interesting compounds. So in the absence of optical conductivity measurements, well, what is the other thing you could do? So here's what they did. So they assumed that you can describe the DC resistivity using Drude-like model. Okay, maybe that's oversimplification, but you do the best you can. And this is the DC limit of the Drude resistivity. N is the carrier density, m star is some effective mass, E is the charge, and tau is what I denote there as the transport scattering time. Okay, so inverse 1 over tau transport is the scattering rate. Okay, so now in the experiment, you try to get m star from some independent measurement, maybe quantum oscillation, specific heat. You try to get the carrier concentration from Hall or again, quantum oscillations. And then, in a regime where the resistivity looks T-linear, you assume that this has a form like that. And yeah, this is just an assumption. Actually, there are even more assumptions that I talk about in the notes. You're trying to extract a scattering rate from this finite temperature region where you see the T-linear resistivity. You're also trying to extract m star from an asymptotically low temperature measurement. So you're assuming that m star itself is not temperature dependent. Now, for those of you who were paying attention in Peter's talk in first week, he did give us explicit example where this is not true, helium, cobalt, indium 5. But anyway, right. So there are all kinds of approximations you've made, but the interesting thing is, even after you do all this, you do this analysis for all these different compounds. This diagonal line is where alpha is order 1. And these very distinct compounds, they all land exactly on top of this line, okay? Of course, one of the greatest tragedies of this interesting regime of T-linear resistivity is, again, the fact that electron-phonon scattering also gives you the same power law. And, all these simple metals that you see up there, copper, silver, gold, they also have a Planckian scattering. By the way, this is something that was appreciated by Pyards in the 30s. So, there seems like there's something interesting going on. And the question is, what can we say about it? Okay, so that was, at least the case for possible existence of bounds on scattering rates, or maybe something else that's related to transport. Now, just so that you don't get too excited, I'm neither going to give you a mechanism for the T-linear resistivity in the cuprates, nor am I going to give you a microscopic mechanism for T-linear resistivity in TPG. And I'm also not going to be able to prove such a Planckian bound on some scattering rate. But I'm going to actually, by looking at explicit examples, I am going to raise more questions. And perhaps thinking about those questions might lead us to some answer. Okay, so by one of you. Okay, so this is, on the case for possible existence of bounds on scattering rate. Now, I don't know if this is just a coincidence or if there's something deeper, but if you look at all of these compounds here, these, parent states of high temperature superconductors. Okay, now the moment I say high, you have to ask me, high compared to what? Okay, and of course, as you very well know, at least as a theorist, I don't care about high in an absolute sense. I'm always thinking about how a high in a relative sense. Okay, so given some intrinsic energy scales in the problem of interest, how high could TC be? And again, this is perhaps also not a purely theoretical question. It obviously has some practical relevance. And again, in the absence of any theory for superconductivity in correlated settings, beyond BSS or Migdal, Eliashberg, how could you possibly come up with some generic bounds on TC? Well, you again turn to experiments. And it was pointed out by very careful analysis that if you look at all superconductors, there does seem to be a wall that you hit. Okay, you cannot exceed superconducting transition temperature that goes above some intrinsic energy scale. Now, what is that intrinsic energy scale? So here, there's a reason I put, again, Fermi temperature in quotes, because extracting a Fermi temperature from an actual measurement is not that straightforward. Okay, so what was done to come up with this table is, again, something quite similar in spirit. You measure the carrier density from some measurement. You measure m star, also from some experiment. And then you just basically use the standard formula for a Fermi temperature that you know for a Galilean invariant system, and use that as a proxy for TF. And again, the interesting thing is if you do that, everything seems to be bounded by that line, which is TC equals TF.
I'm sure some BFT friend would love to write a paper, improving on that.
Sure. And that's probably been done. But actually, this is something that I can say a lot more about, and this will be the subject of tomorrow's lecture. If you use various physical definitions, physically inspired definitions of how you might come up with, what the Fermi temperature in the system might be, fundamentally, there does not exist a bound on TC over TF unless you're dealing with an interacting Galilean invariant systems. Okay, so we'll see how that comes about. But superconductivity is not boundless, and in tomorrow's lecture, I will be able to tell you, what is the fundamental quantity that bounds TC, at least in two-dimensional systems. Okay, good. Any questions? That's mostly, the experimental motivation for why we even think about bounds. Yeah. Yeah, it's for those who really want to think about some BEC mechanism for superconductivity.
In terms of the system parameters?
I think I don't remember the details, but it's probably, again, the standard expression for the BEC transition temperature you would get for some Galilean invariant systems, and you were just trying to plug that in. Yeah. Oh, those are all the strongly correlated systems of interest. So like if you look at it, the cuprates, the pnictides, heavy fermions, they all lie in that shaded region. So there's a trend, and then you are asking whether all strongly correlated systems are really limited by that bound. All right, good. Any other questions? Okay, so actually, in the remainder of today's talk, I want to discuss examples of a very special class of unconventional metallic states that I would like to call as infrared incomplete non-Fermi liquids. What I mean by that is the following. So I'm looking for all kinds of mechanisms that might give me a T-linear resistivity, but only above some temperature scale, T star. Okay, and no amount of fine tuning can really turn T star all the way down to zero temperature. Okay. Of course, we've already discussed the most well-known example of such behavior, which is just the T-linear regime you would get from electron-phonon scattering above the effective Debye or Bloch-Grunwald temperature scale, depending on whether you're scattering off of optical phonons, acoustic phonons, and so on. Okay, but turns out there are more interesting and somewhat more generic ways of getting T-linear resistivity, above some characteristic temperature scale. And these can be in very strongly correlated regimes where you don't have to use the crutch of Fermi liquid theory or the existence of well-defined Landau quasi-particles and so on and so forth. Okay, and this actually also is going to address some of the questions that were being raised earlier in Luca's talk regarding how do you measure diffusion and so on. Yes. What is there? Sorry, what? Wait, rho zero is some potential constant offset. Sorry, and A is the slope of the T-linear resistivity. Okay, so right. So now, I guess you saw Boltzmann theory quite a bit in the first week. And if you remember, there were all kinds of assumptions that went into, what do you put in the collision integral and so on and so forth. And I don't want to rely on that for discussing the first, most generic mechanism for getting T-linear resistivity. And I want to go back to the basics, and that's just Kubo formula. Okay, so within linear response theory, what I want to do is I just want to write down, a generic expression for the optical conductivity. And for the purpose of our discussion, both today and tomorrow, I'm only going to focus on the real part of the optical conductivity. So I'm not going to write, real every time, but it's understood. And so, well, Luke alluded to this yesterday. You can relate this to a correlation function, a retarded correlation function of the current response. And I believe he also assigned this as an exercise. And I encourage you to do the same exercise. Now, what I didn't ask you to do is to rewrite this thing in the layman representation. So I encourage you to do that. And so if you do this, this is what the full expression for the optical conductivity as a function of frequency and temperature. Okay, so here I'm dealing with a system whose many-body eigenspectrum, the states themselves are represented by n and m, and their energies are represented by E of n. Okay, so now if you stare at this expression, so this is just the matrix element of the current operator, which you can get out from your microscopic model. And if you look at this expression, you notice that the only temperature dependence really comes in from here and from here. Yeah. Yes. Yeah, here actually I don't even care about just the ground state. I'm saying the entire many-body spectrum. Okay, right? Because I am interested in the transport as a function of temperature. I haven't told you yet whether the temperature is low, high. I'm interested in the response at all frequencies. So this is why this is the expression over the entire many-body Hilbert space. Yeah, so J is the current operator. So if I give you a specific microscopic model, you can evaluate what the current operator is. And we'll see an example of that in a second. Any other questions about this? So yeah, if you've never derived this, this is a good exercise. Okay, now it turns out, regardless of what Hamiltonian I give you, as long as the Hilbert space for that is bounded, so take any electronic Hamiltonian, of course it has some bounded Hilbert space, there's a way to get a regime of T-linear resistivity at high enough temperatures. What do I mean by that? Well, just look at this expression and take the limit where beta, which is inverse temperature, is where T is the largest energy scale in the problem. So beta is the smallest energy scale in the or inverse energy scale in the problem. And you just expand all of these factors that depend on temperature in a high temperature series expansion. Okay, and we'll only be concerned with the leading order term of that. Okay, additionally, let's also look at the DC limit. So you take the limit of omega going to 0. Okay, so let's first actually take the limit of omega going to 0. You expand this, the omega, yeah. Let me move to this side. I want to leave the screen on because I want to go back and forth and show you some data. So if you do this, yeah. No, I'm going to get to that in a second, yes. Thanks. Okay, so I'm imagining doing a high temperature expansion, but again, I'm not actually going to do a systematic expansion in all powers of 1 over t. I'm just going to be satisfied with the leading order term. And if you do this, okay, and really, I'm also interested in the limit where you take omega to 0. Now, the important thing to note here is this prefactor that comes about just from this term here. Okay, so if you now calculate the resistivity, which is the inverse of that, you get, sort of a trivial regime of T-linear resistivity. But of course, in reality, this is a very complicated system. Imagine I give you some complicated Hamiltonian. Let's take the Hubbard model as an example. It's possibly in some very strongly correlated regime where U is comparable to or even larger than the bandwidth, but you're at very high temperatures. So this is like T-linear resistivity that is showing up in a very ultra-hot regime, but nevertheless, it's there. Okay, so let's first look at whether this is relevant at all. Now, again, the important point to note is this is something you obtain when the temperature is larger than the bandwidth. Okay, so in the cuprates, you're certainly not seeing evidence of this when I talk about T-linear resistivity. Actually, for that matter, this is not relevant for any electronic solid because you always have to deal again with phonons. But as it turns out, you can look at a very interesting system which can be probed experimentally. And this is also going to address questions of how do you measure diffusion. So this is a cold atom simulator where they're literally just taking the Hubbard model with some nearest neighbor hopping and on-site Hubbard interaction. There are no phonons. You know the microscopic model really well. And this is also part of what is known as this quantum gas microscope. I'm sorry I forgot to put the reference here, but they're in the notes. And what you really do is you measure the diffusivity and the compressibility, okay? And then what you do in order to get a resistivity is go back to the basics. Actually, maybe I should. Use Einstein relations that relates all of these three quantities. Okay, so now I'm going to ignore what are known as any thermoelectric effects. So in that limit, the conductivity, the DC conductivity, is related to the charge compressibility times the diffusion coefficient. Okay, and what's done in the experiment is that they have a way to extract the diffusion coefficient as a function of temperature and the compressibility as a function of temperature. And they use that to figure out what the conductivity or relatedly the resistivity should be. Okay, so let's just first look at the resistivity. That's your region of T-linear resistivity. Actually, not quite, because there's something interesting going on. So it turns out this regime of T-linear resistivity is not coming out because of the scattering rate, which is what we started out by discussing, being linear in T. Okay? In fact, the scattering rate or the diffusivity is temperature independent. Instead, what is giving rise to the temperature dependence is coming from the compressibility. So again, how do you see that? So I'm going to leave that as an exercise as well. But again, within a high temperature expansion, if you calculate the thermodynamic charge compressibility, you can convince yourself that that goes as 1 over T. Okay, so yes.
On 5T expansion, but
Yeah.
I might worry from that formula that until beta is where 1 over n, where n is the number of particles in the system, that like this expansion is sort of baffling the cases there.
Yeah, so I agree. Actually, I can't remember if one of these lines, which is taken from the paper, is related to some high temperature Yeah, there are all kinds of questions. I agree with that. I mean, this is supposed to really be an asymptotic high temperature regime. In fact, something I was going to get to is, yeah, let me get to that in a second. You know, the dotted line that you, actually, is there a pointer? Maybe I'll use this. The dotted line that you see here is the expected 1/T contribution to the compressibility. So, you know, depending on the data that you're seeing, you might be tempted to believe that the compressibility is approaching that asymptotic limit. But you know, if you think about it, 8 times T, not that high, and especially the expansion is supposed to work really at temperatures above the many-body bandwidth. That's where the N that Andy was talking about comes in. But nevertheless, it's promising. But actually, the mystery here is not that there exists a regime where this high temperature T-linear resistivity shows up. But if you look at the data, especially, let's first look. Okay, maybe it's 1/T, but then it's exhibiting some non-trivial temperature dependence. Okay, if you look at the diffusivity, it is maybe constant out here, but it's definitely picking up some temperature dependence. In fact, it looks like it's becoming 1/T. The temperatures at which the crossovers start to rise, they're different. But when you combine these quantities to reconstruct the resistivity, it doesn't look like there is a dramatic change in the slopes. Okay, so why is that? I don't know. But one can go back to the expression for the conductivity that I wrote down, and it has the temperature in all kinds of places. You can ask yourself, what is it about generic models that will give you such a nice single regime of T-linear resistivity without any crossovers? What do you need for the current matrix elements and your many-body spectrum to look like in order to get this nice single regime of T-linear resistivity? Again, that's largely an open question, but some progress has been made. Again, I give some references. Yes?
So that's really in the high temperature.
Yeah. Yeah. So that's why I said, you take any model with a bounded Hilbert space, and with a conserved U1 charge so that you can define a conductivity. At truly high temperatures, they all give you T-linear resistivity, and it's because of this. In the experiment, it has to. Yeah, because it's related to the many-body bandwidth, right? Yeah. Which is, I don't remember how many particles they had here, but yeah. So yeah, me too. So yeah, in fact, I guess maybe, yes, of course, yeah. In fact, so from that, it's unclear if this thing and this thing that you're seeing are reflecting the high temperature expansion regime. And so again, the interesting thing is, why do you get this T-linearity? No, it depends on the many-body bandwidth, right? So that depends on.
Well, this effect is not at such high temperatures, it depends on the volume of the system.
But that's
Yeah, I don't. So why do you see that same T-linear regime persisting?
Because they would.
Yeah, I don't know.
Data on, I could easily fit a two slope, like two different slope. The errors are huge. What are we talking about?
Okay, yeah. So that's.
The concept of linear in general, but I mean, this figure, I don't. Okay, sort of fit. Other things also fit.
Yeah. So it might just, yeah, that could be, and it might also be a coincidence. In fact, next I'm just going to talk about something where as a function of temperature, all kinds of smooth crossovers might even stop looking like distinct regimes. I'm going to give you an example of that in a second. So yeah, and some of these same questions are even relevant for something very different, which is maybe there's something similar going on. Maybe there is, and there's a paper that came out recently with regards to electron phonon scattering. If you have many different phonon modes, all the different crossovers that you might expect using some Mathiesian rule, they might just get rounded off and you don't see any crossovers. So when you're thinking about finite temperature, strong correlation regimes, many of your naive expectations, may be too simplistic and may not be, what's going on in experiments. Yeah. I mean, I wish there were follow-up experiments here, but unfortunately, they moved on to other things. So, yeah.
This high T scales with your system size. And let's say they have 100 atoms here, then H does not seem high enough.
Right. I should go back and look at how many atoms they had. And it was definitely smaller than, yeah, okay, let me not try to remember what the system size was. Yes. Oh, it's some different theoretical methods they use, DMFT versus Lanczos versus, yeah. Yeah. No, so the interesting examples where we care about T-linear scattering rates are where the compressibility becomes constant and the diffusivity has all the temperature dependence via the scattering rate. And that's what we really want to get in, the kinds of models we write down for, your favorite material. But of course, measuring compressibility or diffusivity in electronic solids is a highly non-trivial task. Except that in recent times, there are some measurements in 2D materials where this has been done. At least in TBG, this has been done. Sorry, was there not? Yeah. So this is the DC resistivity. Everything here is in, yeah, but here, as I said, you want to take really the limit of omega going to 0 as well. Yeah. Like think about, what you draw in the Drude theory. You draw something like this. This in the limit of omega going to 0 is your DC conductivity, yeah. Oh, no, very different. Right. You mean in normal metals because of electron phonon scattering? Yeah, no, very different. Again, there it is the electronic scattering rate that is T-linear. Whereas here it's, again, this ultra high T is dominated by the compressibility being temperature dependent.
Very common, about 500 atoms.
Okay.
Yeah.
And the system size? I see. Yeah, okay, well, so yeah, there are lots of puzzling things about this experiment, but in general, what I want to move on next is, is such a regime where you get an inverse T compressibility and a temperature-independent scattering rate or diffusivity only possible at high temperatures, or is this something that can show up due to more interesting mechanisms in, sort of not contrived models, and models that look, relatively realistic? And I want to talk about an example of such a model. Okay, this may not be a model of a real electronic solid, but actually it has a number of nice properties that actually makes it even solvable. Okay, so I'm imagining the following situation. So imagine I give you a triangular lattice. Okay, that looks more like a Kagome, but okay. Imagine that it's the two triangles meet. And I have a bunch of spinless fermions. Okay, so spinless electrons that are hopping around on nearest neighbor sites with some amplitude. And these are spinless electrons, so the simplest interaction that you can write down is a nearest neighbor repulsion. Okay, and I have a chemical potential that couples to the density, and so I can tune my filling. Okay, so I can go all the way from of 0, so no fermions, up to a filling of 1. Okay, so now I want to think about, what are the possible interesting regimes of transport in this material. Now, if the interactions are weak, and I start out with some nice, Fermi liquid and turn on a weak interaction, even without doing any calculation, I can basically guess what the answer is going to be. At low temperatures, I'm going to get a standard Fermi liquid-like behavior with a t-square resistivity, whose coefficient depends on some dimensionless combination of the V's and the T's, okay, just because of Umklapp scattering and so on. That's not the regime I want to analyze. I want to understand some very strongly correlated regime, okay? So I want to think about the regime where V is much, much bigger than T, okay? And by the way, this model, as far as I'm aware, it's never been really solved exactly because, for instance, this stuff from the sign problems, you can do Monte Carlo. If you're thinking about really transport, you probably want to go beyond ED and so on. So, the low temperature or the low energy properties of this model, I don't think are known. But you can do an interesting strong coupling expansion, and you can almost get exactly solvable results for the following reason. Imagine if I switch off the hopping altogether, okay? Does this model remind you of anything? Ising model, okay? It's the antiferromagnetic Ising model on the triangular lattice. And a lot is known about that for many decades, I think for the 40s. I mean, Wannier and then Stephenson, Fisher, and so on and so forth. So I want to leverage the property of this very strong correlations and properties of this antiferromagnetic Ising model. So of course, you have to make the association that the charge density maps to the Ising variable and so on. And the magnetic field is like the chemical potential. And I want to think about transport at some intermediate range of temperatures in this limit where V is much bigger than T, okay? So now I want to think about transports. In order for me to describe transport, electrons have to hop around, okay? And I want to think about transport perturbatively in T. So if you think about it, the current itself is proportional to T. If I switch off T, there's no hopping. And the conductivity is going to be order T squared. Okay, so now if I want to go back to this expression, and I want to calculate this thing, okay, starting from this strong coupling limit by turning on a weak hopping, the T squared is basically something that comes up front because of the J squared. Okay, so now I still have to evaluate all kinds of correlation functions, but the correlation functions themselves can be calculated with respect to the T equal to 0 theory, which is just my plain old antiferromagnetic Ising model. Yeah.
That point of view doesn't matter whether it's a triangular lattice or a square lattice in terms of strong correlation, right?
Yes.
But can I go to a spin model somehow?
Yeah, because what I want to say is if you have these frustrated, very strongly correlated models, they can give you a solvable, interesting regime of T-linear resistivity with some what is known as bad metallicity. So I want to, do this in a very simple fashion. I mean, yeah, you can do this on a square lattice, and actually that was also done with some slightly different properties and so on.
Right, but on the mapping to antiferromagnetic Ising, right, that depends on a specific choice of mu relative to T. Because I could also think of this as like a hardcore lattice gas on the triangular lattice, and that
right.
All frustrated necessarily.
Yeah. So when mu is 0 at half filling, it's just the nearest neighbor antiferromagnetic Ising model for which a lot is known. And then you're imagining turning on, a field which, takes you from, you can sweep the densities. And, the hardcore boson model actually was solved exactly because that model does not have a sign problem. I will show you what the phase diagram looks like. The model is truly only solvable analytically when mu is 0.
But I still then is like exactly solved. Still kind of a mess, but it's been done.
Yeah, but it's been done. So yeah, like mathematicians, you can claim that now it's mapped to that problem, and I assume it's, solved. Right, so now what I want to do is just, do this perturbative treatment and, rewrite what the expression for the conductivity looks like. And again, this is left as an exercise. And so you notice how we wanted to solve the problem in strong coupling for a weak T. And we only care about the leading order corrections at order t squared to the conductivity. So I already have that. So now when it comes to evaluating the rest, I can evaluate it with respect to the theory that does not have a hopping, just the pure interaction model, which is sort of a very correlated classical liquid. And okay, so again, notice how I'm describing transport in a metal, but I am not alluding to any underlying Fermi surface. It's really short distance physics with very short range correlations. I'm literally thinking about how the electrons hop around in this lattice and contribute to the conductivity. So how do you think about this? This is the piece that I already explained. Now, in order for the electron to hop around, what is this thing here? You're basically counting the probabilities associated with whether an electron is already present at R and the site at R prime is empty, and these hops are allowed. Okay, and you're starting out with some configuration of occupancies in your system with some energy I, with the electron at site R. You want to go to a site where the electron goes to site R prime, and these have to differ by some energy. Okay, so you're really just trying to calculate a histogram of sorts associated with these kinds of hoppings. Okay, and then you calculate this thing, and then you can extract the conductivity of the whole system. Yes, initial and final associated with these hopping processes. Yeah. So when the electron is located at a site R, which wants to hop to a site R prime, this is the initial energy with that configuration, final energy associated with that full configuration. And you're sampling this over all the different configurations associated with the electrons. Okay, so yeah. You're basically so this is a completely classical computation. You're basically doing classical Monte Carlo associated with all kinds of different configurations of the charges. Of course, with some, if this were fully filled or fully empty, then there's nothing to describe. But if there are places that electrons can hop around, you just go ahead and calculate this. Is the setup clear? Sorry, yeah, so sorry, I forgot to say that. Here I'm imagining that if you go back to that picture for the triangular lattice, you're calculating the current in the x direction. So there is some, vector associated with the current in that direction. That's what D represents. Yeah.
The inner sum is over all configurations that are connected to the configuration for which you calculate the Boltzmann weight.
Yes.
By one.
Yes, exactly. Yeah. Okay, so this seems, somewhat interesting, not the usual kind of transport regime, and we can do this. Now, before I show you what the actual data looks like, this is what you expect the system to do. Okay, so if you're at temperatures, again, V is much larger than T, the hopping. If you're at temperatures much above V, then it's some uncorrelated classical gas. When you cross over through the scale where temperature is of the order of V, this is where the electrons really start feeling the effects of the correlations. You're going into some correlated fluid. Now, as I will show you, there's a very strong tendency at a filling of a 1/3 and 2/3 for the system to develop charge density-like correlations, again, because when the nearest neighbor repulsion is strong, you want to avoid each other, and that leads to all kinds of crystalline order, okay? And so, of course, in this setup, when you're doing perturbation theory in little t, everything that I say, it will only be limited by temperatures of the order of T. I can't go below an energy scale of the order of T. Okay, so this is what the result looks like. And the first thing you can do is just calculate the compressibilities. And again, what this shows is there are distinct regimes, and the compressibility exhibits all kinds of non-trivial crossovers. So this is sort of high temperature expansion with the 1/T. Now, why did we start talking about the solvable nearest neighbor model? Because in this limit where you switch off the hopping, and let's say you're at mu equal to 0, which is just the antiferromagnetic Ising model, the magnetic susceptibility of that Ising model maps to the compressibility of this model, okay? And for which there are a number of results that are known. This dashed line that you see is precisely that result. It's also 1 over T, and that's because just the nearest neighbor antiferromagnetic Ising model, it doesn't order, okay? The susceptibility is 1 over T all the way down to 0 temperature, okay? And so you see crossovers from a high temperature trivial 1 over T to some correlated low temperature regime, okay? And also if you happen to be exactly at 1/3 filling, the compressibility drops because that's where you're really going into this insulating CDW-like regime, which is dominated by the nearest neighbor repulsion. Okay, now if you calculate the conductivity, just by evaluating this sum using Monte Carlo, you see all kinds of interesting behavior. Importantly, you do see different kinds of regimes of T-linear resistivity, which are controlled by the compressibilities in the two different regimes, okay? But if you look at it closely, as you're varying the filling, there exists some intermediate region where you would have thought they would be very distinct slopes. They're not. They're smoothly connected. There's nothing profound about this, but it's just that, when you're looking at the finite temperature properties, you can have smooth crossovers, and there might be some intermediate regime where the slopes just line up. Yeah.
What's the ratio of little t and v?
That's arbitrary. That's up to you.
Oh, so
Because little t here only enters as a prefactor, except when you calculate these histograms, when you do the binning, the smallest resolution that you really have is set by t, little t.
I thought that we were doing things conservatively in little t.
Right.
On top of big V.
Right, and the leading order expression, the only place where t enters is this, and the rest is evaluated with respect to the t equal to 0 theory.
Oh, that's the conservative.
Right.
Okay.
Right.
Yeah. Something that's capitally bigger than
Oh yeah, of course, yeah. T is like the smallest energy scale here, so t can be arbitrarily small with respect to V, but you can go down to temperatures, of order T and not below. So this is still high temperature, but this shows that the frustration, okay, because of strong electronic correlations, can give you new regimes of T-linear resistivity, but still no T-linear scattering rate. It's all dominated by the compressibility and strong correlations. So very different, presumably, from what we are after in the context of cuprates or TBG and so on, but interesting nevertheless, yes. No, it's dark magic associated with that solvable point of, yeah, let me leave it at that. Any other questions? Yeah.
Okay, compressibilities are 1 over T always above. So here it'll be above V.
No,
you don't need the number of particles.
No, but here it's really tied to the fact that in the original Ising model, the magnetic susceptibility, in the absence of a field, really just goes down as 1 over T all the way.
Oh, so that's just, okay.
That's the property of the frustrated Ising model that I'm leveraging. Which, yeah, and that susceptibility maps to the compressibility, yeah.
Is that classically correlated?
Yes.
There's nothing quantum mechanical.
There isn't. In fact, if you were to do the same calculation for charged bosons, of course, the ground states are going to be very different for these two sets of models, but this regime remains the same. Yeah. Yeah, because, you should think about it this way. It's the particles that are hopping around, and you're really capturing all these transitions associated with individual hops. The statistics really doesn't matter. You only need to solve this model between 0 and 1/3 or and 1/3 to 2/3, because then there's some particle hole symmetry. So yeah, in this model, it's quite generic that there's some intermediate filling where this kind of had to happen. Yeah. Right, so that those, so let's look at green here and green here. these different slopes are really controlled by these different regimes of the compressibility. Yeah. Right, so in the low temperature regime, it's this property of this Ising model. So, let me just write down what the Ising model is. It's just J sigma I sigma J on the triangular lattice. If you look at the magnetic susceptibility, so, dm, dh, that goes as 1 over T. And the magnetic susceptibility now maps to the compressibility.
You switch. All right.
I mean, if you take some frustrated square lattice, which in this classical limit shares the same feature, then yes, you would get the same behavior. Yeah.
On the map, I see that n equals 0.17 curve, the blue curve is we can still see kind of a change in the behavior. It's not exactly straight, but the plot on the right is saying n30 is very straight, just because of the scale of the plot on just some different.
Sorry, could you repeat that again? I didn't catch the first part. Yeah.
That seems not exactly that straight. We can still maybe see.
Yeah.
But on the right, it seems very straight.
Yeah, and that's the miracle of gradual crossovers and finite temperature physics. Somewhere in between, yeah, you don't really see clear demarcation between different regimes.
Yeah, also this susceptibility is looks like a single spin susceptibility. Just a spin susceptibility for single spin.
Yeah. Yeah.
So if I'm not considering a frustrated phase, I'm just the spin systems and then gradually add popping terms. Do I still expect similar behavior?
Yeah, okay, that's a very simplistic picture of what's going on. Really, what I'm leveraging here, this is not the density correlation that determines what kind of processes contribute to the conductivity are also determined by the 2-point correlations of that original Ising model. And for this frustrated Ising model, they are non-trivial. So the 2-point correlations do affect the transport. It's not just dominated by purely a single, yeah.
But T much bigger than V, surely they are.
Yeah, of course. But that's the totally trivial regime. I don't need this model to
But
really.
Is there a physical way to understand the regime below temperatures below the V? Is there some scale out to which are normalized and that think it's just a single spin but reduced?
I'm not sure.
Reduced by 5 over 36.
I'm not sure. I don't think so, but maybe something worth thinking about. Yeah, Sungun. Oh, yeah. Read the paper. I'm not going to discuss it. It'll take me off on a tangent. Yeah, it has to really. Yeah, it also has to, intuitively, it has to do with you're developing these CDW-like correlations. So, how charge moves in the background of those CDW correlations is complicated. So, yeah.
Like I think it's probably you have very rare particles.
Exactly.
That can't be in the
Right.
CW and those.
Right. Yeah, we discussed that in the paper. And actually, I think Leonid had a paper from long back talking about very different things where he also talks about similar physics. Okay, that's all I'm running way behind, but that's okay. Okay, so all these examples were meant to illustrate examples of very strongly correlated regimes where, by the way, I forgot to mention this, if you look at the actual magnitudes of the resistivity, these can exceed h over e squared. So these are what are known as bad metals. But again, you don't see Planckian scattering rate. It's all dominated by compressibility in one form or the other. Okay, and of course, I started out by telling you examples of systems of great contemporary interest where you do see Planckian scattering rates. Now, those systems are super complicated. Honestly, if you ask me, I don't even know what is the best starting model that I should write down to describe all the degrees of freedom of which the electrons scatter off of. Okay, so the question that, of course, I've been interested in many years is there some relatively correlated compound where I really know what are all the different degrees of freedom that the electrons are coupled to, where maybe the microscopic parameters are known, which also shows some unconventional regime of T-linear resistivity that I can actually understand from a microscopic first principles perspective. Okay? And turns out there is such a compound. And the best part of studying this material is that one of the biggest challenges with transport is that you can't disentangle the electron-electron scattering from electron-phonon scattering. I just give you the resistivity. How do you know whether it's coming from some conspiracy of the electron-electron, electron-phonon, and so on? And for instance, even in the cuprates, imagine if you had a theory, a purely electronic theory for what gives you T-linear resistivity. I can always ask, okay, so now what happens if I start add phonons? How will they affect the scattering rate? Okay, so inspired by all these questions, we started looking at these materials. I want to tell you a little bit about what these compounds are. So this particular compound made a brief appearance yesterday because at low temperatures, there's been some discussion of whether or not it shows hydrodynamic behavior, but that's going to be irrelevant for what I'm talking about. I'm going to talk about intermediate temperature phenomena. So you have these materials, known as delaphossites, which have been pioneered in Andy McKenzie's group, which basically consist of the following. So it's quasi-2D. You have these layers of palladium, which are metallic. And then you have different kinds of insulators sandwiched in between. Okay, so we are going to look at two different compounds, one that has a chromium oxide versus cobalt oxide. Okay, now the fermiology looks almost identical, but these intermediate layers are very different. So cobalt oxide is a band insulator. It's a vegetable. We don't need to care about it. The band gap is of the order of electron volts. Chromium oxide, on the other hand, is a Mott insulator. Okay, so it's a triangular lattice, again, which has local moments sitting at the site of the triangular lattice. Okay, so now at low temperatures, the fact that you see these shadows, that has to do with the presence of these local moments. I will not get into the detailed description of that. I can talk about that offline. Now, chromium and cobalt, if you remember your periodic table, they're pretty close by. Okay, so their ionic masses are quite similar, which means if you look at the phonon spectra of these two materials, they're also reasonably similar. Okay? Any questions about the material? Okay, and so this is what transport looks like in palladium chromium oxide. Okay, so at least there is some intermediate range of temperatures. This is limited by, I believe, the temperature of the furnace. And it just goes on and on up until that temperature. If you do the same Chowdhury-like analysis, you get a scattering rate that's Planckian with an order 1 coefficient. Now, if I just gave you this compound, you would say, well, why not phonons? This might be consistent with phonons. I forgot to say that there exists some temperature around 40 Kelvin where the local moments in the chromium layer actually order. Yes?
So does the chromium oxide also exist in isolation form? So when you say that chromium oxide is a Mott insulation,
yeah.
What do you mean?
Oh, from magnetic measurements, it exhibits Curie-like susceptibility. And in neutron scattering, we've measured the spin correlations.
And no charge fluctuations?
No. Yeah, so the Mott insulator is not doped by the palladium electrons. Yeah. Yeah, resistivities are either much smaller than or much bigger than h over e squared, which is 25 kilo ohms. Equivalently, KFL, where KF is the Fermi momentum, L is the mean free path, much smaller than or much bigger than 1. Yeah. Oh, that's this analysis I told you before. So here you measure the DC resistivity, fit it to a Chowdhury-like form. You know N, you know M star from some other measurements. You fit it. Yeah, it has all its, that was the first part. Yeah, it has all its assumptions, approximations. And maybe the interesting question is to ask, in spite of all this, why does it always turn up to be order 1 coefficient? Any other questions? Right, so if I told you nothing else, you could have said, well, this is all phonons. But then, oops. Oh, okay, I guess my slides got switched. You look at this other compound, the sister compound, which does not have the local moments. So that's the red curve here. Okay, so the phonon spectra are almost identical, but their resistivities differ by quite a bit. And the chromium compound is the one that exhibits a T-linear resistivity. Okay, now if you take, if you believe that you understand palladium chromium oxide essentially as palladium cobalt oxide plus some other scattering mechanisms via some Mathieson type rule, then the green curve is the difference between the two scattering rates. So it's whatever would arise because of the difference in their ionic masses. Because the structure is the same, it's just instead of chromium, you have cobalt. All right. Now, okay, before we start interpreting things in terms of Mathieson, maybe it's good to ask if there is any indication of Mathieson-like behavior. And this is where, one way to test at least part of this question is to do the following. You take your material and you bombard it with some radiation, okay? It's a very violent process, I guess, to me, but okay, depending on your perspective, you might say it's not, but it's doing all kinds of things, maybe introducing defects and so on. And generically, you might have thought that it would completely screw up the temperature dependence of the resistivity, but this is what happens. As you increase the dosage of radiation, all that it does is just shift, only changes the elastic contribution, which of course you expect to change if the impurities are changing. The slope remains the same. By the way, this is something has been seen also in the cuprates. This is YBCO, very old data. So there's some similarity between the two sets of results. Not to say that what I'm about to tell you in Delafossites has any bearing on cuprates, but still worth noting. Okay, so the question is, what is causing this excess scattering, and why do you get a T-linear resistivity in chromium oxide? So, whenever I talk about this, I always like to, I'll tell you a possible explanation, but I always like to hear if someone has any ideas. What are the suspects that might lead to this Planckian T-linear resistivity? Hotspots because of the Van Hove, but the Fermi surfaces of the two compounds look almost identical. So you have to invoke something that's, building on top of cobalt oxide. Yeah.
The nuclear spins of chromium cobalt.
And what would that do? I mean, before we talk about nuclear spins, why isn't anyone talking about just the normal local moments? I mean, that's the obvious first step, right? Like, palladium chromium oxide has these local moments sitting on the chromium sites, which the cobalt does not, okay? These local moments are fluctuating. Surely they're coupled to the electrons in some fashion. You're at temperatures well above the ordering temperature, so it's some thermally fluctuating paramagnet. So could that just be it? How many of you think that might be it? High temperature, just like high temperature phonon scattering, right? Here it's high temperature scattering off of thermally fluctuating paramagnetic spins. Good. And how many people think that can't be it? Okay. So why do you think that can't be it?
Spectrum are bounded above.
Right. So this is what I was trying to get at. So, scattering off of phonons, very, very different from scattering off of local moments. And as I emphasized at the beginning, phonons have a completely unbounded spectrum. Their occupation is just determined by the Bose-Einstein distribution. If you're at temperatures well above the Debye frequency, the number of phonons as a function of T goes as, right? So if you take the high temperature limit, this basically becomes T over omega Debye. Okay, that's not how spins work. These are local moments. They have a bounded Hilbert space. There's no sense in which you can create as many spin excitations in that paramagnetic state. Okay, so in high temperature limit, as the electrons are scattered normally fluctuating paramagnet. The scattering rate, the temperature dependence of that is going to saturate. Okay? So that can't be responsible for this enhanced T-linear resistivity in palladium chromium oxide. Yeah?
What about the excited state of
I'm not sure I understood. Like, so basically, it's again, it's not unbounded. So yes, spin 3/2. You're talking about what happens if I start exciting these. Yeah, but right, but again, I mean, first of all, I think these splittings are huge. I don't remember what they are. Certainly not enough to give you the T-linearity over this temperature window.
That's at 10,000 Kelvin.
Yeah. Okay, so what could possibly be going on? Okay, so that's what I want to talk about in the remaining 10 minutes, I guess. And really, the point of this is to show that it is actually phonons, but phonons entering in some weird ways. Okay, so not the standard electron-phonon scattering, but phonons can get intertwined with electronic degrees of freedom in all kinds of interesting ways. And yeah, don't just discount phonons altogether from the beginning. Okay, I mean, I think, didn't Maslov have a very interesting theorem in his notes where point one was phonons always exist in electronic solids, and number two was if you don't believe, go to point one. So yeah, phonons are there, and we should think about them seriously. Okay, so before I tell you how to think about this, the beauty of the other reason why this is a great system to look at is because the low energy microscopic model of the Delafosse is very well understood from a combination of spectroscopic measurements, etc. So what you really have is just the itinerant electrons associated with the palladium layers. And the chromium, as I said, it's a strongly correlated degree of freedom. This is the Anderson type model. We'll ultimately be interested in the Kondo-like limit, but the hybridization to begin with is described by some hopping between the palladium and the chromium layers. But of course, in reality, since the local moments are well developed, you don't think about these charge fluctuations. You describe it using some Kondo type model. Just for the sake of concreteness, I will write it out. So you have your epsilon k minus mu palladium and Kondo coupled to the chromium spins. And then there is some super exchange between the chromium spins as well. Okay, and all these coupling constants are actually known from some fits to the spectral functions that I could come back to if anyone's interested. Okay, and as I said, this by itself is not enough at these high temperatures to explain where the T-linear resistivity might be coming from. Okay, there are of course also phonons here, but these phonons are the same as the cobalt oxide, so they're not going to be able to explain where the additional resistivity is coming from. Any questions about the model? Okay, so now the puzzle is where you're getting the excess scattering from. And, sorry, it's actually connected to something that's quite physically. You have these two things sitting in different layers. So originally, I said, well, there is some tunneling of electrons between the nearest neighbors from the palladium to the chromium. Okay? But who said that this can't have additional corrections that depend on the actual displacement between the two layers? Okay, so when the electrons hop, it's not very rigid. I mean, these integrals could themselves depend on the separation. And if these ions are vibrating, it can couple to the phonon displacement. Okay? Now, if you redo the Schrieffer-Wolff transformation that takes you from here to here, you get an additional piece, which is basically alpha jk s chromium dot p agar sigma P that's modulated by precisely that out-of-plane phonon displacement. So this is an example of an magnetoelastic coupling that modulates the Kondo interaction itself. Okay? Any questions? X is the phonon displacement between the two layers. Yeah.
This only exists in all systems.
Yeah, it's just a question of how large is this effect. And yeah, I've been trying to convince DFT people to try and compute it from first principles. It's a complicated three-body interaction, but is the physical origin of this clear? Okay, with this we're basically done. So we're again going to assume that this high temperature regime where you're seeing the T-linear resistivity is associated with this out-of-plane phonon displacement being in its respective quasi-elastic regime, where the phonon occupation associated with this guy is given by just T. But the good thing is you can do a much more detailed calculation, a full-blown Boltzmann calculation. And okay, this is what the dotted lines versus the solid lines represent. The dotted lines are data. The solid line is a actual Boltzmann calculation with all the known microscopic couplings, with the only fit parameters in the theory being the strength of this magnetoelastic interaction and the characteristic frequency of this out-of-plane phonon displacement. Okay, so you can describe the data, but that's not why I'm talking about this. There's something weird and interesting that comes out when you do this analysis, okay, which may or may not have some bearing on these Planckian bounds, which is what I want to discuss. Okay? Yeah. The out-of-plane phonons? So, first of all, this is something I'm making up. I don't know directly from experiments. You can assume either one. For the high temperature, it doesn't matter. I mean, the onset temperature matters. But of course, the low temperature regime matters. So actually, yeah, it turns out in this particular example, if you assume acoustic phonons, the low temperature regime can give you a T squared and not, if you think of this as 2D and not T to the fourth because of some interesting mechanism for momentum relaxation. But yeah, so I mean, for the high temperature regime, it could be either. In reality, which one it is, I don't know. I mean, there is some, but not all the phonons have been analyzed carefully, I presume. And that's something, again, yeah, the experimentalists should try to measure. Okay, any other questions? So the interesting thing that I want to highlight is the following. So what I'm plotting here are the computed scattering rates that you would get just from purely electron phonon scattering, and the combination of the Kondo scattering, the electron magnetoelastic scattering, and so on. Okay, now if what we want to explain is this green curve, that's the difference between cobalt oxide and chromium oxide. Okay, if that was the only T-linear contribution in the story, then you would have expected a straight line. But it's not. What you're really seeing is palladium cobalt oxide is doing this weird thing. Actually, we understand exactly where this is coming from. This is due to coupling to two phonons, one of which is in the high temperature, the other one is not. The green is the difference. And miraculously, when the two add up, that's what the scattering rate in palladium chromium oxide looks like. Okay, and this is the one that's almost linear with this Planckian value. So for some remarkable accident or maybe some deep underlying principle, it's as if all these scattering rates in a fashion that gives you this Planckian scattering rate, which is T-linear, which of course we don't understand. And yeah, that's a mystery. So what is the conspiracy going on? Is this just related to some chemistry, some stability? There have been suggestions to that effect, at least for purely electron phonon models, that there is only so much that you can crank up an electron phonon coupling that gives you the high temperature T-linear scattering rate before the system becomes unstable. But here, notice that the bound is not just on an electron phonon. The bound is on the total scattering rate that adds up to this thing here. So that's a mystery. Why is that? I don't know, but maybe one of you can figure it out. Now, is there any indication for why this might actually be the right story for this compound? And the answer is sort of yes, at least it's promising. And that's because you can look at thermal transport. Okay, and if your scattering is quasi-elastic at in the temperature window, for instance, where you see the T-linear resistivity, you would expect Wiedemann-Franz ratio to be satisfied. I mean, if you think about the original Wiedemann-Franz experiments, they were done at room temperature, right? And indeed, in this compound, L over L naught approaches 1, roughly in the regime where you see T-linear resistivity. So you know that the scattering is quasi-elastic, most likely due to some phonon-induced mechanism, but just not the bare one. The local moments are involved in some way because you have to explain this excess scattering in chromium oxide. Okay, let me not go into this because there's also evidence that in the magnetic compound, the phonons actually soften to some extent. Okay, so the coupling to the correlated electronic degrees of freedom leads to a reduction in their effective Debye temperature scale. Okay, so why did I talk about this other than the fact that it's one correlated compound which has local moments where you can come up with a pretty accurate microscopic theory? Because now I want to just raise the following set of questions that you should think about. So we ruled out phonons as a possible explanation for these unconventional strange metals because they can't explain T-linearity down to low temperatures. How do you explain Matthiessen or the absence of Matthiessen? And why is it that they only show up in certain points, optimal doping and so on? But now imagine that phonons are strongly coupled to the electronic degrees of freedom, right? So it's a strongly coupled problem. Is it conceivable that, of course, everything is being driven by the electronic correlations, but the electrons themselves somehow soften the phonons, and then the T-linear resistivity that you see is due to these softened phonons that pushes down the scale where it's seen. And it's only some phonons whose coupling gets enhanced, again, because of electronic correlation effects. And they are the ones that contribute most to scattering and not the other ones, okay? I mean, a lot has to happen. And these are just words right now. But at least this is something that there's one other person in the room, or actually two other people in this room who are thinking about with me. If you want to blame it on someone, blame it on them. That's how you and Shuopeng. So I think I'll stop here. Yeah.